Well, we talked about inverse functions, or reminded ourselves about inverse functions yesterday. Let's now create the inverse trig functions. So we'll start with inverse sine. And a reminder, the -1 notation for inverse functions does not mean 1 over. Okay, that is inverse function. So we'll start with the sine curve itself. We know its domain is all real x, we know its range is in between -1 and 1, but clearly it fails the horizontal line test. It has no inverse. We want to pick a piece of this curve that is continually increasing or continually decreasing. Now we've got lots of choices there for a section. We want to try and include the origin, get as much as the range as possible. And theoretically, it should always be possible to get the complete range, because you could restrict the domain in such a way where you go, I'll go between this point and this point, but then I'll also go between this point and this point, and you get the whole range. But here, the choice seems fairly straightforward. If we'll go just in between -π/2 and π/2, we're going to get a complete range. We've got something that's continually increasing and includes 0. It looks like a good choice. As I say, the range will not change. Our inverse function then is y equals the inverse sine of x. The domain now will be -1 to 1, and the range will go between -π/2 and π/2. It'll be the reflection in the line y equals x, but because of my scale here, because there's 1 and there's pi, it's probably easier if I just do it on a separate diagram. We're going from -1 to 1, -π/2, so it's a sine curve, or a piece of the sine curve, but now we're winding along the y-axis instead of the x-axis. Oh, it's a little bit dodgy, but there it is. There's my sine curve, or inverse sine curve. Inverse cosine then. Let's do the same thing. Once again, I want to pick a section that's continually increasing or continually decreasing. I can't do the same one I just did for sine, because between -π/2 and π/2, it's going to fail that horizontal line test. So I'm going to choose a bit that's continually decreasing. I'm going to go from 0 to pi. That'll get me the complete range. Includes 0, which I like. I'll tend to go with the positives rather than the negatives. So we've got our complete range. Inverse cos, domain -1 to 1. Range now is 0 to pi. Again, we would reflect in y equals x. And there's our cosine curve winding along the y-axis. Now this explains our calculators now. Why is it that when we plug a negative number in for sine, or inverse sine, we get a negative acute angle? Well, that's because of the graph. It's using that function, and its range was -π/2 to π/2. Whereas cosine will give us the obtuse angle, because we're using the inverse cos curve. And so we do get an obtuse angle with our calculator. Let's complete the set. Let's do inverse tan. Draw in y equals tan x. Once again, fails our horizontal line test. Choice here is quite easy, really, because all we've got to do is go in between two of our asymptotes, and we've got a lovely continually increasing curve. It's going to cover the whole range. So that's what we'll do. And obviously it's not including π/2 for this one because of the asymptotes. And we'll get a range of all real y. Swap them over. So now my domain's all real x. My range is in between -π/2. Reflect that one through y equals x. And we will end up with a tan curve, but now, well, I don't know if it's true to say winding for this one, but it's going along the y-axis rather than the x-axis. So there's our three basic inverse trig graphs. So what do we notice? It now means this relationship must be true. The inverse sine of -x must equal the minus of inverse sine of x. Well, look at the picture. It's an odd function. It's got the rotational symmetry. Cosine's a little bit more interesting though. Cosine of -x will be pi minus the cosine of x. We've got an odd function that's shifted up pi/2 units. So I'll explain that in a sec. I'll complete the set of identities here. Inverse tan of -x will be minus inverse tan of x. Again, we have that rotational symmetry. It's an odd function. And this relationship must be true as well. Inverse sine of x plus the inverse cos of x must equal pi/2. Certainly if we're talking about a right angle triangle, one angle is going to be the inverse sine of x, the other angle would be the inverse cos of x, and we know the angle sum of a triangle is 180 degrees, or pi radians, so therefore those two must be pi/2. So how do we get this inverse cos relationship? There's the inverse cos curve. Let's say it's an odd function that's been shifted up pi on 2. So let's move this back down pi on 2. So my red curve would be the inverse cos of x minus pi on 2. But that is an odd function. We've got the rotational symmetry. So because that is an odd function, it must be true that function negative x is equal to the negative of function x. Therefore, the inverse cos of negative x minus pi on 2 must equal the negative of the inverse cos of x minus pi on 2. Playing around with that, moving terms over, and we get our relationship. And that's why it's pi, not pi on 2. Even though the shift is pi on 2, the actual value in the identity here is pi. Some alternative notations. So I've used the one with the -1 there in the position that traditionally we put the power for trig. Some people prefer to write arc sine, so you don't get that confusion with the power. Very rare, but I have seen it. A sine, rather than writing the whole of the arc. I'd probably avoid that one because that really looks like you're saying a times sine x, like a being a single pronumeral. So I think that one can be a bit confusing. But you'll notice it, and it's very subtle. Notice how my a is not in italics, and that's how you would tell the difference. Because pronumerals, of course, we would write in italics. We now have to find the exact value of the inverse tan of root 3 minus the inverse tan of 1. You're going to see these numbers come up a lot because they are our exact values. We're basically saying, well, what angle gave me the answer of root 3 and what angle gave me the answer of 1? But it has to be the inverse tan curve. So whilst there's many different angles that could give us root 3, there's only one when we're talking about the inverse tan curve. So it'll be pi on 3 minus pi on 4, which is pi on 12. Inverse sine of 1 on root 2 minus the inverse sine of minus a half. Well, that's the one where I've got to consider the curve, because inverse sine will only ever give me an acute angle or a negative acute angle. So because it's negative a half, it must be giving me a negative acute angle. The acute angle that would give me the ratio of a half is pi on 6. So I get pi on 4 minus pi on 6, 5 pi on 12. I suppose alternatively, you could have said the inverse sine is an odd function. So the inverse sine of negative a half is the same as the inverse sine of a half. Negative becomes a positive. You get the same answer. The cosine of the inverse sine of 40 on 41. Remember, when we're talking about inverse sine, inverse cos, or any inverse trig, that is an angle. So we're saying the cosine of an angle here, 40 on 41. Personally, I just think of the triangle. Go, all right, there's an angle in this triangle that is the inverse sine of 40 on 41. That means its sine ratio is 40 on 41. Yeah, a bit of Pythagoras. I'll get the other side's 9. So what's the cosine of that angle? 9 on 41. Other way around. Inverse sine of the sine of 5 pi on 6. Now this is where we've got to be careful, because it's very tempting to say, well, the inverse and the sine, they'll cancel each other out, because that's what inverses do. It's an inverse sine that we're finding, and we can only give answers out that are in its range. And the range of inverse sine, remember, negative acute angle or positive acute angle. 5 pi on 6 could not be the answer. The answer would be pi on 6. How do I know that? Well, 5 pi on 6 is in the second quadrant. I know sine's positive in the second quadrant, so it must have been the positive acute angle that I got there. So 17b, let's play with our inverse trig result.